Okay, I'm going to go ahead and get started. So today, what we're going to do today is we're going to be whiteboarding worksheet 2. We'll do one of the problems on worksheet 3, but we won't do all of them. And then you'll be ready to take the impulse momentum test, and I'll kind of talk about that a little bit at the very end too, and also remind you that you can do practice AP test. So let me go ahead and show you worksheet 2, what you're going to be working on. We've already started some of these problems, and I think the problem we're getting ready to do is number 4. So this is a file that was shared with you last week. We've done problems 1 through 3. We're getting ready to do problem number 4. I don't really care if you do the part A using the momentum conservation diagram. That's fine. You don't have to do that if you don't want to, but I definitely want to see the conservation momentum equation, figure out how big the impulse is on the car, and also figure out the velocity of the boy after he jumps off of it. So let me stop sharing. I think I need to put some of you still in breakout rooms, so give me a second. Okay. Okay, so let me go ahead and open up the rooms now for you. Again, oops, everybody's in. Again, you're gonna be working on problem number 4. Sorry, there's a couple more people coming in.
Do you say number 4?
Problem number 4, worksheet 2.
All right, thanks.
Okay. Oops, one more person coming in. Sorry. It's just easier to let them in now. Okay, so let me go ahead and open up the rooms for you. Problem number 4. Okay, I think everybody is back, or pretty close to everybody's back. I'm just gonna kind of share my screen with you so that we can just look at one person's in random. Okay, so let's see. All right, first of all, I want to share with you my picture. Oh boy, can't see it down there. All right, so I'm hoping that you kind of sketched a picture, or at least you get a picture in your head. You really need to do that. It's not hard, and so I think it would really help you out to make sure you don't make any mistakes. Not that these are hard, but I mean they're so easy. You don't want to make mistakes on them, right? So, boy, I don't know where to put this at to make it go away. There we go. All right. So before I kind of have that on the left over here. The boy is riding on the cart and they're moving at some speed v here. Okay. Afterwards, the boy jumps off and his speed is 0. But the cart keeps on going, and I hope that you see that the cart must be going faster now to conserve momentum. And so we're going to be looking at part B, C, and D for just some group I'm going to pick at random here. All right, so how about this one here? Okay, so the momentum equation they have is basically the initial momentum of the system. They separate it onto the boy in the cart equals the final momentum of the boy in the cart. Nice. And then realize part C. If you want to figure out how big the impulse the cart gets, well, it's going to be equal and opposite to the impulse the boy gets. So that's what they did here. They figured out the impulse on the boy. So it'd be 70 times 0 minus 70 times 2. So MVF minus MVI. That's the impulse on the boy. So all you have to do to figure out the impulse on the car is it's equal and opposite. So it's 140 meters per second, 140 Newton seconds in the same direction, in the original direction. That's my picture. Notice the cars are going much faster than it originally was going. Okay. And I think it was this group, wasn't it? Yes. And then finally, to figure out the velocity of the car after they jumped off, they just used the conservation momentum equation up here, plugged in the numbers, and they got 4.8 meters per second compared to 2 meters per second. Yeah, it's a lot faster. It's over double. So, any questions? Anybody have any questions? You might have to unmute yourself if you have a question. All right, so then the next question we're going to be looking at is number 5. Number 5, we have two girls that are facing one another on skates. So they kind of have their hands together like this and they're just sitting there, and then they push off one another, okay? Part B says write the conservation momentum equation. Part C says find the impulse. I want to give you one more part. It doesn't ask for it here, but I want to know what is the velocity of that larger girl, the 70-kilogram girl. It gives you the final speed of the shorter girl, the smaller girl. I want to know the velocity of the larger girl too. It doesn't ask that. So give you one more part, part D. Before we do that, could you please all kind of unmute yourself? What kind of event is this? Remember, we have elastic collisions, we have perfectly inelastic collisions. What kind of event is this? You might have to unmute yourself.
This is
An
a
elastic
explosion.
explosion.
Yeah, I think I heard at least one person I heard say explosion. This is like an explosion. Yep. Okay, so let me stop
Okay,
sharing this. A question first? No. Okay.
no, I was agreeing.
Okay. This is number 5 we're doing. So B and C for sure, and I'd like you to also find the speed of the bigger girl. So let me stop sharing and open up the breakout room. Krishna, you should have got invitation to breakout room 9. If you didn't, you can go ahead down the bottom and just join 9. Luke's already in there. Okay, so again, I'm going to show my screen. If you have questions, just ask me, okay? Or butt in, no problem. So let me share my screen with you. I'm going to share my picture first because I want to talk about something here. So here are the two girls. They're pushing off one another. The top picture is right when they're starting, before the explosion, and then afterwards, they're moving away from one another. I also put this other point on here. I'm calling it CM. That stands for center of mass of the whole system. So you can see that the center of mass in the top picture is a little bit closer to the bigger girl because she has more of the mass. Okay. You should think of the center of mass as kind of like if you could somehow magically balance this system of these two girls on your finger, that would be the place that you could balance it at, the center of mass. We could usually when we draw a force diagram, we pretend all the mass is located at the center of mass. Okay. What I want you to notice is look at straight below. Both the girls are moving away from the center of mass. The one on the left moves a lot further away than the one on the right, but the one on the right does move. If you look at it, she's a little bit further away than she was in the top picture. The reason why the one on the left is proportionally further away is because her mass is proportionally less. So it's just simple ratios to figure out how much further away she is. It's kind of like momentum. It's all about ratios. But mostly what I want you to see is how that center of mass doesn't move. It stays exactly where it's at. In other words, in the second picture there, again, if you could somehow, let's say, put both of these girls on a very thin plank that has no mass to it whatsoever in that picture, in that second picture, you could actually balance it right on your finger right there at that center of mass. Um, the center mass idea will not be on your impulse momentum test today, but you could see center mass stuff on the AP test on Monday. It's kind of Unit 5 stuff, so I'm hoping that some of you have been looking at the Unit 5 material. It's really kind of easy to do calculations on it. I gave you a link for a whole bunch of Unit 5 materials. It's not really that hard. It's kind of proportional kind of stuff. It's ratios and stuff. So it's not that hard. I definitely encourage you to look at it. Um, but anyway, the most important thing is you'll notice that center mass, it doesn't change. And so really this whole idea of conservation of momentum is kind of based on the center of mass is momentum is not changing for the system. All right, so I'm just going to pick one at random here, one of the groups. Got to get this out of the way so I can read it. So the conservation momentum equation they have is the initial momentum, which is 0, they have there, is equal to the final momentum of the system, which would be mvf for object 1 plus mvf for object 2, the two girls. They calculated the impulse, and the impulse they got was, so that would be mvf minus mvi would be 500 kilograms times meters per second, okay? Which means the impulse on the other girl would be the same, except it would be in the opposite direction, equal and opposite. So I guess if one's to the left, the other one would be to the right, 500 kilograms times meters per second, or yeah, 500 kilograms times meters per second. By the way, you could also have Newton seconds there too, right? And then they did conservation momentum equation to figure out the velocity of the girl, and it's 7.143 meters per second. And since it doesn't have a direction up here, I guess I'm okay with this negative. Um, Try to be a little bit more descriptive on the AP test on Monday, though, if they ask you something like this. Say something like she's moving at 7.143 meters per second in the opposite direction of the lighter girl or something, or more less massive girl, something like that. Any questions on this one? Okay, so the next one we're going to be looking at is number 6.
Oh, I had a question.
Yep, Daniel, go ahead.
So the center of mass thing,
Yes.
would it kind of look similar, like in relation to the 0? Would like the center of mass be on the 0 in both, since it's
Yeah.
that's like conservation, whatever?
Yeah. So, like, for instance, if you want to say the center of mass is at the origin, then no matter how long you've been watching this movie where they're exploding apart and there's no friction and they're moving further and further apart, that center of mass of those two is always going to be on the origin. It'll stay exactly where it's at.
Okay, yeah, thank you.
Okay, I want to keep on going with that because really Daniel had an interesting question there, and I want to go a little bit further. I wonder, is there a way I can ungroup these? Ungroup. So let's say, dang it. Just give me a second, sorry. All right, this is going to be a pain. All right. Why is it not ungroup these things? Okay, group. Okay, and then, oops. Just be patient for a second. Definitely going somewhere with this. I think it's kind of cool anyway. So let's say that here's the before, and this time the before is also moving. So let's say this whole thing, let's say they're moving like this, right? And they're getting ready to push off one another. Well, whatever velocity that center of mass has before the explosion, after the explosion, let me see if I can move these over here. So now I'm going to move them together. Let's see. I'm not sure how I can do this. Let's see. So remember, before the explosion, the top picture is moving to the right at a constant velocity. After the explosion, that center of mass is still going to be moving to the right at that same velocity. Now, true, this bottom girl here is going to be kind of going like this, and this girl here is going to be going kind of like this, but that center mass, whatever velocity it had before, it's going to have the same velocity afterwards. Daniel, can you say yes if you get that?
Yes,
Okay,
yes.
thank you. Because that is a good question. Because if you get that, that could be super, super, super helpful. Because basically it says if you know what the center of mass is and you know what its velocity is, it's always going to be the same. So for instance, let me give you another example that sounds even more complicated, but once you understand this idea of center mass, you're like, whoa, that makes things so easy. Imagine you had a projectile. Remember, we did projectile stuff, and all of a sudden it gets to a certain spot and it explodes there. So it's an explosive projectile, and you have like three parts. One part goes this way, one part goes like this, and one part gets shot like that. If you're like, I don't know how to figure out where they land at, the truth is the center of mass will still follow that parabola. And so as long as you know where that center of mass is and you know what those initial velocities were away from that, you should be able to figure out where any of them land at. I've seen that on an AP problem once before. I don't know, that could be a good one to practice. I don't remember. That's definitely on the AP Central website. If you're interested, send me an email and I'll see if I can find that one for you. All right, so the next problem we're looking at is problem number 6. This one's kind of like a William Tell thing, except it's not with an apple. Somebody's going to shoot a arrow through a melon. It's not going to get stuck in the melon. It goes through the other side of the melon. It's slower now, and the melon will end up falling off the person's head. So what I'd like you to do is, you don't have to do A if you don't want, but please do part B, and also do part C, find the melon speed. So let me stop sharing and open up the breakout rooms. Okay, I'm gonna go ahead and share my screen again. And again, if you have questions or something, please say something as soon as you think of it. Don't waste time trying to remember it because you might end up forgetting. All right, let me share my screen. I think I'm gonna show my picture first. So again, it's not an apple on top of the head, it's a melon, but that's kind of the picture I have in my head. And then down below, that picture on the left is kind of my initial, so before this event. So the arrow is coming toward the melon. After the arrow goes through the melon, it's slower now, and the melon is moving. So I have a question, if you could unmute yourself for a second here. What kind of event is this? Remember, we have like explosion, we have, elastic collision. What kind of event do you think this is?
Perfectly
Inelastic
inelastic.
collision?
So I heard perfectly inelastic. What else?
Just normal inelastic, not perfect.
Yeah, I think it's normal and elastic.
Okay, what would it mean if it was perfectly inelastic?
The
They
arrow
stuck
stayed in the
together.
melon as it just like went off the guy's
Yeah,
head.
they have to get stuck together, right? So if the arrow got stuck inside the melon, then it would be perfectly inelastic. Okay. So the truth is, though, I heard a lot of people said just inelastic. That would be my guess too. The truth is, even though you're like, okay, we know for sure it's not perfectly inelastic because they're not stuck together. We also know it's not an explosion. But the truth is, you never know for sure if it's an elastic collision or an inelastic collision. I feel pretty confident this is inelastic, like most people said here, because my guess is there's probably some kind of thermal energy from friction when it goes through there. But you got to remember, this is a made up problem. These numbers are totally made up. It's possible that the person who made up these problems made it such that energy is conserved, because that melon is huge, right? I mean, it's a big melon compared to the arrow. What's the only way for sure that you can tell if it's an elastic collision? Elastic. Go ahead and unmute yourself. How do you know? Anybody know?
If it
The arrow
bounces
has a
off.
slow speed.
Well, it's not like you can look at the problem and say, "Oh, I know." You have to do a calculation. What kind of calculation would you have to do?
Perfectly inelastic equation. Is that what you're saying?
Uh, no, it has nothing to do with momentum. That's your hint. It has nothing to do with momentum. When you use the word elastic, there's only one way you can tell for sure if it's elastic. You can't read the problem and go, "Oh, that's elastic." Nope, you cannot tell. You have to do a calculation to figure it out.
Energy.
Yes, Antonio, that's right. You have to calculate the energy. So I'll show you in a second because I want to make sure that you understand it. It's not hard to do, but you need to understand that the only way you know for sure is you have to do a calculation. So anyway, I'm just going to pick somebody at random here and see what kind of answers they got. So here's their momentum equation right up here. And then they calculate it and they got a velocity of 0.3 meters per second. Okay, so I want to show you what I mean by doing the calculation. If it's elastic, which we're all pretty sure it's not, then what that means that EK initial equals EK final. Okay, so I want to show you what this would mean then. So initial is going to be 1/2 times the mass of the arrow, which is 0.05, times the initial speed of the arrow, which is 30 squared. And the melon's not moving, so that would just be 0 kinetic energy, equals, and then 1/2, or actually, I don't know if it equals, right? So I'm going to put equals question mark, right? I don't know. So 1/2 times 0.05 times, let's see, 18 squared, and then plus, it's going to be 1/2 the mass of the melon, which is 2, times, we just calculated the speed of the melon is 0.3, so 0.3 squared. So can you guys go ahead and do that calculation very quickly on the left-hand side and tell me what you get, and I'll do it too. So the initial energy, somebody quickly find that. .5 times 0.05 times 30 squared. What do you get?
22.5.
Okay, 22.5. Can I get a verification on that? Oh, where'd it go? I'm typing. It's not going. 22.5.
That's what I got as well.
Cool. 22.5. And we're going to see if it's equal to the final energy. So the final energy, can you do this calculation? Is 1/2 times 0.05 times 18 squared plus 1/2 times 2 times 0.3 squared. What you get?
I got 8.19.
8.19 joules. I agree. So they're not equal. So is this elastic?
Eight.
Is it-
No.
No, it's not. It's
No.
not. It's not elastic. This is called inelastic. So some of that energy that it has kinetic, now it's thermal energy or something like that. Any questions on that? All right. So, okay, then we're getting ready to go to worksheet 3. So let's see if I could pull. I shared that with you, I think, yesterday. And I looked at worksheet 3 already. Most of these you should know how to do. There's not a whole lot of interesting ones, but I kind of thought number 2 is a little bit interesting. Again, I don't care if you do the conservation diagram. I don't care about that, but I definitely want you to do the part B and part C. Here's the reason why I think it's a little interesting. Let me see if I can kind of get you to imagine this. We have this truck going down the road too fast, and it's catching up to this car that's not speeding. And the truck driver is not paying attention. What happens is the truck driver rear ends the slower moving car, makes the slower moving car now move faster, and now the truck's moving slower. So it's kind of a different event than what we've seen before, slightly. So if you can please go ahead and do problem number 2 on worksheet 3. Okay, so let me stop sharing and open up the breakout. Okay, again, I want to share my screen with you. Before I do that, I think I actually want to kind of show my picture that I have. Come on, stupid thing, sorry. This picture, this is always in my way. All right, so I've got this truck that's moving at a certain speed here on the left-hand side. That's the before collision, and the car in front of it's moving slower. Afterwards, now the truck is over on the right. The truck is now moving slower, and probably as a result of that, the car is going to be moving faster. In fact, it says that speeds up. So I'm just going to, hopefully I'm not picking the same people all the time. I'm going to pick somebody here at random. So they said the initial momentum is equal to the final momentum. So they figured out the initial momentum of each vehicle beforehand. So they got 70,000 and 15,600. And afterwards, the final momentum would be of the truck 60,000 plus the final momentum of the car 1,200 times BF, and they solved for the speed of the car 21.33 meters per second. By the way, some of you aren't getting these answers, so I hope you're really looking at this and you're asking questions. You're not getting it, okay? Sometimes I leave notes on your whiteboard, so you might want to go back and check to see if I said something, okay? One more thing I want to check is, actually, can you guys unmute yourself for a second? What kind of collision do you think this is, or maybe something you know for sure it's not? How about that? We'll start with that. What's something you know for sure it's not?
Not
Non-explosion.
perfectly inelastic.
Not explosion. Not explosion. What else? It's not.
It's not perfectly inelastic.
Not perfectly inelastic, which means we have two possibilities. What are they?
Inelastic and inelastic.
Elastic.
That's right, inelastic and elastic. And the only way we can tell for sure is we have to do what kind of calculation?
Energy.
Kinetic energy.
Yeah, kinetic energy. So I want you to look over here. So let me get rid of this. So the top here is the initial, 1/2 the mass of the truck times 14 squared plus 1/2 the mass of the car times 13 squared. I didn't put in the masses. It gives you the masses up here. I just didn't put them in. And then afterwards, it would be 1/2 the mass of the truck times 12 squared plus 1/2 the mass of the car times 21.3 squared. Can you guys right now in your calculator go ahead and do those calculations for me really quickly? Maybe write them down, the two answers.
Cookies are done.
Cookies are done. Is that what you said? Who's got cookies? Adam, you got cookies? No.
Nope, they're mine. They're going off in the background.
Make me jealous. Okay.
So for the initial, I got 59. Wait.
Is that what you got? 59?
Yeah.
591,400?
Yep.
Okay. And can somebody also do a calculation for the final then too?
I got 632, 981.34.
Okay. I just rounded a little bit. So I'm hoping other people check those out. And I also, since you got your cameras turned off, I hope you're really paying attention to this. Put down the cookie, Adam. So I want you to look at this. The initial energy is 591,400 and the final kinetic energy is 632,900. It's like we gained energy. That's one of the problems with doing, that's one of the things that teachers have to be careful of. Physics teachers need to be careful of when they make problems up. Because with momentum, you got to be really careful with the speeds and the masses and stuff. And I didn't take very close attention here, but I want you to see this. So in effect, we gained energy. How could that possibly happen? Can somebody with a fanciful thinking brain, can you think of something that could have happened in this collision that maybe gave it more kinetic energy?
There's no friction? I don't know.
Well, even if there was no friction, it couldn't have got more kinetic energy. It would have just simply stayed the same. And then we call that elastic collision. We would have called that elastic. But this is definitely not elastic. But I'm trying
downhill.
What, say that again? Oh, yes, that's a good idea, Kyler. You said going downhill? I think it was Kyler. So going downhill, yeah, going downhill, that's a possibility. The only thing I could,
Sudden gust of wind.
a sudden gust of wind. I like that one, Henry. Mine was, let's see if you like this. You can see what kind of movies I like to watch. Mine was this truck hit the gas tank of the car in front of it, and there was an explosion. We had chemical energy being converted into kinetic energy. What do you think?
Yeah.
I don't know. There you go.
Could have been.
All right. There you go. All right. So we don't really have any more, but I do want to talk about one more problem, and that's number 3. We're not going to whiteboard it because it's not really any different. We have a radium particle here that's setting off on the left-hand side, and it decays. There's a nuclear decay, and what happens is it turns into radon and something called an alpha particle. That's a fancy name for saying helium. So if you ever had a helium balloon, it's filled with a bunch of alpha particles. We don't call them alpha particles anymore because they're not ionized and they're not moving really fast. They're just kind of sitting still, sort of. So helium is the same thing as alpha particle. Anyway, these two particles shoot away from one another. So what kind of event is this sort of like?
An explosion.
It's an explosion, yeah. So I don't really want to do this one because it's kind of like ones we've done before. But I want you to understand that if you're interested in a Large Hadron Collider or a Fermilab near Chicago, the kind of stuff they're doing is looking at conservation of momentum and conservation of energy. That's all the stuff that they're doing. So if you really understand that stuff and you really like that stuff, I mean, there's a path for you there in physics, I think. There is one thing I want to talk about related to this problem, though, that you won't see on your test after class, but you might see, I mean, maybe you might see on Monday on the AP test. There's only 2 questions, though, so I doubt it. It probably won't be on there, but, you know, maybe. I just want to make sure I talk about it. And that is, let's say instead of radium, let's say we have some other particle that's just sitting there and it explodes into 3 other particles. We call those other particles, by the way, if you're into particle physics, we call that those daughter particles. Let's say it explodes like this. How is this picture that I have here different than this one up here? Besides the fact there's 3 of them. Do you notice that the one up here is just simply one-dimensional? It's in the X direction. Whereas this one here is in kind of like the X and Y direction. I'm hoping, can I get a thumbs up or something that you see that?
Yeah.
Oh, okay. Okay. All right. So the only difference is, it's not really any harder. The only difference is that you're going to have 2 conservation momentum equations. You're going to have initial momentum in the X direction equals final momentum in the X direction, and you're going to have initial momentum in the Y direction equals final momentum in the Y direction. It's not really any different. You might have to do some trig. There might be some angles involved, but it's kind of easy because the initial momentum before the explosion is 0. So it's not really that much more difficult. All right, so now let's talk about, uh-oh, I lost my tab here, sorry. Let's talk about then the test. Hey, went right to it. Don't know what happened to it. Let's talk about the test then. The test is going to be open all, wait a second. Am I on the wrong page? Yes, I am, dang it. Sorry, give me a second. The test is open all night, all the way to midnight. You can do it multiple times, but and it's not really a 100-point test. In fact, it's not even, it's only 38 points. And actually, it's only 36 points. You get 2 points of bonus. So it's more like a quiz, I guess. But you need to understand that there's 8 narrative items. I wouldn't really call them essay, but sometimes you have to explain something. The computer can't grade those. I have to grade those myself, but I'm not going to grade every submission you have. I'm only going to grade the last one. But the other items that are like multiple choice or fill in the blank kind of stuff or a calculation kind of thing, that will grade it automatically, and that's 22 of the points. So I think if I were you and you're trying to get the best score possible and you want to retake it as many times as you want, I think I would just look at your score at the end, and that part is out of 22. And if you got 22 out of 22 and you feel pretty comfortable about your narrative, then I wouldn't worry about doing it anymore. Okay. Let's see, what else do I want to talk about? Oh, I'm going to talk a little bit about the AP test on Monday. Again, on Saturday, you should get your code. You can do more of the demo problems. If you watch the video here, you can check out doing an example problem. I'm hoping you picked up the packet because I had some problems in there that you can kind of practice doing. I do want to talk a little bit more about doing submissions, especially if you got my packet. Because in my packet, not only did I have the 3 example problems, but I had my typed out responses. I imagine there's some students that are like reading through that and going, yeah, that's not my strength. I can't do that. But I could definitely draw force diagrams. I feel more comfortable doing that. I feel more comfortable doing mathematical stuff. I totally get that. So my suggestion to you is figure out right now before Monday, figure out which method is better for you. Is it better to type out your answer? Do you feel comfortable doing that? Or, and that's what I'm recommending. But if you're like, I can't do that, I'm not going to have any success, then I recommend then, yeah, go ahead and get some paper, put your AP ID and your initials at the top and the page numbers. And I don't know, can you guys see that? Let me stop sharing the screen here. And take a picture of what you have there. Make sure you write legibly as possible. Take a picture of it. And this is what I'm recommending. Instead of taking a picture and saving it as a JPEG or something like that, they just had an update. And evidently you can save this as a PDF. So rotate it, save it as a PDF, and then upload that PDF. The reason I'm saying that is the nice thing about PDF, they'll see your text, what you're writing, I should say, what you're writing, but they also see your free body diagrams and equations and stuff. I'm still recommending, based upon what I've heard, I'm still recommending you type it out. But if you're saying I can't do that very well, then I guess what I'm saying is instead go ahead and make a picture, rotate it, save it as a PDF, and upload it that way. If
So,
that,
sorry.
yes. Sorry, who's Dan? Is that you talking? Yeah.
Yeah. I was just gonna say, because if we're using the picture method, is it okay if we take a picture of our phone, or should we just do it with a computer? Because I know that earlier you were talking about how it's a bad idea to use like 2 devices on the same test because that could look like cheating or something like that.
Right. Okay. So here's my understanding. You can use your phone. Okay. So let's say you access the test on the computer.
Yeah.
You can take a picture of your work with your phone as long as you're not accessing the test with your phone. So in other words, you'll take a picture of it and you'll send it to your email or something on your computer and get it that way. You could do that. That'd be fine. I need to tell you a couple things, though. The problem with that, though, idea is that adds one extra step. Whereas if you just take a picture with your computer, that kind of cuts out the middleman. It's one less step, I should say. And
Right.
I'm also recommending, just in case you guys didn't hear, is that once you take that picture, you save it as a PDF, because you need to understand right now that if you save it as just a picture on your, JPEG or whatever,
Mm-hmm.
the reason they're doing that as a JPEG or GIF or whatever the 3 methods are is because they have certain plagiarism software, and what it's going to do is going to use some OCR, optical character reader software, that's going to look at your writing and turn it into characters, and they're going to look for plagiarism. That's the only reason why they say those 3 formats. But they recently just said, oh, and the reason why I mentioned that is it won't see your force diagrams or equations or anything. It'll only see what you've written. But if you save it as a PDF, not only will they be able to use the OCR software to see you didn't plagiarize, so in other words, they can read your writing, but they'll also be able to see your pictures of your force diagrams and stuff like that. Now, I'm not, again, I want to just emphasize, I'm not saying that you should do that way. I'm saying that try to do type, copy, and paste. Try to do that. But if you're not comfortable, my recommendation is take picture, rotate it, save it as PDF, and upload. Okay. Whichever method you're going to do, you need to practice it. Remember, I've got that website. In fact, let me go back to, I just want to show you again. So, come on, why is this not sharing?
The demo?
Yeah, right here's the demo. You really should try. Okay, let me see if I can save it as a PDF and upload it. Let me try that. And so I just recommend that you give it a try. The other thing I want to say is you need to take at least Sunday off and don't do any practice of AP Physics. You just need to take the day off. If you want to do something on Saturday a little bit, okay, but take the day off on Sunday. You should not be cramming. Any other questions you guys have?
So the packet questions are the same one that are on the AP website, but it's just hard to find, kind of, right?
Yeah,
That's what you're saying?
Yes, I find it very difficult to use their website, and so
Yeah.
I thought students would feel the same, and
Yeah.
so that's why I printed it out in the packet. Plus, I printed out the scoring guides that's in the packet because I felt those were also hard to find, and I thought maybe students couldn't find it. And this is something that's not on the website. I typed up my sample response of if it was type, copy, and paste. I did a sample one for each of those, so you can kind of see. Because one of the things with the scoring guidelines is it doesn't really say what the answer is. It kind of just gives you these are the things we're looking for. So, and so it also has the AP check sheet in that packet, and it has your equation tables that you can use in that packet.
I just wanted to try out the submission ways, that's all.
Yeah, you should definitely do it. Oh, I just remembered something else. I might have mentioned this already, especially for people who are thinking about the cell phone method. If you have an iPhone, you have to get in there and mess around with things. iPhones usually save things as HCIM or something like that, and you can't do that. You have to change it, and I don't know how to do that. You have to look that up. So, all right. Any other questions?
I don't think so.
Okay, well, good luck, everyone, and I'm sorry we're kind of ending on this note, and I wish I could see you in person, but I guess this is it. Good luck. If you have any questions over the weekend, give me an email.
Will do. Thank you, Mr. Linfesti.
Bye.
See ya.
Love you, Mr. Linfesti.
Love you too. How's that cookie, Adam?
I didn't have cookies.
Oh, I thought it was you. It said it was cookies.
I wish it was me.
Oh, okay. All right. See ya.
See ya.
Any question, John? No? Okay. Okay. See you, John. Ethan, did you have a question for me? We're all done.
I was just making sure. I just left and then I thought, oh, he might be taking a picture for attendance.
No, that's all right. Okay. We're all done. I just didn't know if you had a question. Okay.
Right, no, thanks.
See ya. Bye.